Okay, so question 47, give the major product of each of the following reactions. There are actually 6 sub-questions for this 147, but I'm just going to do 3 of them just to get you kind of going on the right path. So for each of these questions, again, one thing to keep in mind is that the questions are not asking you for a mechanism. So if you don't want to draw any arrows to show electron movement, you do not have to do that. All they're really asking is the major product. So, but if you want to go through a mechanism to make it easier on yourself or harder on yourself, I don't know, it depends on the way you think about mechanisms. You're more than welcome to do them if you'd like. So I'm just going to go through them. I'm not going to do any mechanisms. I'm just going to figure out the final product by the rules that we have. Okay, so for this question A, we have this cyclohexene right here, this methyl cyclohexene, and we're just going to have a basic reaction with HCl. This can happen with HBr as well. And so all we're going to do is we're going to have our basic addition mechanism. So this is a nucleophile, electrophile. We're going to put our hydrogen on the carbon that has the most number of hydrogens. So just going through that, this carbon down here has 1, this one has 0. So H is going to go here, chlorine is going to go here. So if we're going to redraw this guy, we would draw the products like this, where we have 1, 2 hydrogens right there, and the chlorine on top. And you can rationalize this using a mechanism. Remember that this HCl addition goes through a carbocation intermediate. So if you really want to know the Y has everything to do with stability of the carbocation. So try to figure that out if you're not comfortable with that. Okay, so this sub-question D is almost exactly the same as sub-question A. We're just doing slightly different, we were doing a slightly different setup with the nucleophile. So instead of adding HCl, we are still adding an acidic compound, this sulfuric acid. But instead of the resulting nucleophile being, attached to the original acid like the Cl was, the nucleophile is going to end up being this oxygen right here. So what we're going to do is we're going to protonate this alkene just like before. And after that, instead of adding a sulfate, we're going to end up adding H2O as our nucleophile. Okay, so same exact thing. We have 2 hydrogens coming off just like this. And after a couple of extra steps, obviously we're going to end up losing one of these hydrogens. And it's always a good thing if you can remind yourself when and why this happens. But the final product is going to be this hydrated alkane. So one of the hydrogens from the water will still be there, the other one is removed at some point during the mechanism. So again, it's really good to just be able to, really quick, be able to predict the product, but it's even better if you can rationalize it out with a mechanism for this kind of addition. And it's very similar to this addition, there's just one extra step. Okay, so finally sub-question E, what we're going to do is we're going to, again, start with the same starting material. We're going to have our dihalogen. We can use Br2, Cl2, although Br2 is the more classical way of doing this reaction. And this is actually quite an important bit, so this H2O. So notice in your book, I believe the reactions are on page 195. There are 2 different ways to add, halogen. You can either do this in protonated solution, or you can do it in an aprotic solution. So something where we can have end up a resulting nucleophile, or something where we cannot. So the alternative to doing it this way is if we had CH2Cl2 or dichloromethane instead of the water, and that's going to give you a totally different result. Okay, but one thing you need to be able to recognize is these conditions promote halohydrin formation. Okay, halohydrin formation. So what we're going to do is we're going to end up forming our, or we're going to end up breaking our double bond just like before. We're going to end up forming our chloronium ion instead of bromonium ion. And after that, the question is, which carbon does the water attach to? So the water is going to end up attaching in a Markovnikov fashion. Okay. So in this case, the nucleophile is going to be the water, and it's going to end up attaching at this point right here. And again, we don't have both hydrogens attached to the oxygen at the end of the day, but during the mechanism, we definitely will end up getting HOH2 plus here. But again, you can prove to yourself why we don't have that via going through the mechanism. So we don't just get this hydration product, we also have one of our chlorines still attached to the bottom. Okay. All right. So again, all of these reactions are on page 195 in Bruce. And this is, again, a very subtle point to make sure you recognize that if we use water as our solvent, we're going to end up having a hydration, versus if we just used Cl2, we're going to get dichlorination. So let's say if we did this exact same thing and we had just Cl2, and let's say we do it in some solvent that is not nucleophilic, so dichloromethane, okay, something like this. Instead of getting this hydrated product or this halohydrin, what we'll end up getting is this dichlorinated product. So chlorine here, and obviously we'll have a hydrogen here. We don't have to draw this one out, but again, it's implicit. If you want to draw it out just for completeness, that's totally your call. Okay, but again, huge difference between this guy and this guy.